Hello and welcome to the third episode in the I-beam trolley series. Now today we will be designing the shaft. We've already done the I-beam and the roller, and the design choices we've made in these two parts are going to inform the design of the shaft as well. But we've also selected the bearing, and that is also going to affect the design of our shaft. So without further ado, let's jump in. So first thing, I'm going to be opening the roller, and I'm going to be opening up the spec sheets for my bearing, and I'm going to go straight for the abatement dimensions, which are here. Right, this is the little drawing. These are the dimensions. Now let's just remind ourselves, this is a 3200 bearing. That means that it has a bore of 10 millimeters, a width of 14, and an OD of 13 millimeters. Now today we're interested in the bore diameter, because that's going to be our shaft diameter, and the width, because we need to make sure that this bearing sits securely onto the shaft. And another detail I might have forgotten to say is that when you have a dual row, an angular contact dual row bearing, it's always good practice to secure it from both sides, on both the shaft and the housing. Whereas with some single row bearings, when you don't want them to be taking serious axial loads on either the shaft or the housing, it's a good idea to leave one side unconstrained, right? So one side floating. That way you're sure that your bearing is not taking any axial loads, and it can't go anywhere, because the shaft is a certain length and the housing is a certain geometry. So probably the shaft will have another bearing taking up axial loads, and so on and so forth. But that's the difference in double row and single row bearings. This can definitely take a lot of axial load, so we're not worried about it. We're constraining it on both sides. So we have the abutment dimensions here, and we have the design of our roller. Let's start with the roller. This is 1.05 inches in length. So that's definitely a length that our shaft needs to accommodate. Behind that, I'm going to have a clearance to the carrier of a 1/16 of an inch. That should be enough. I don't want these two parts rubbing against each other, but a 1/16 should be enough. And then I'm going to have the carrier, which is going to be a sheet metal part. And it's good if you specify sheet metal parts with sheet metal gauges. So we'll be using a mild steel for the carrier, and I want to use the thickest one that's readily available on the market. Pretty sure that a gauge 7 sheet metal sheet is going to be readily available in many different markets and places in the world. And if you think this is too thin, well, it's not that thin. 4.5 millimeters of steel is nothing to scoff at. But there are also tricks in sheet metal parts to increase their strength by quite a bit, and I will be showing them in the next episode, which is the carrier. So basically, to decide on the length of our shaft, we have 3 components we need to consider. 1, the width of the roller, right, which is 1.05 inches, plus the tolerance, 1/16, plus the sheet metal gauge. And I want my shaft to end at the face of the carrier, because I will be specifying that it is welded onto the carrier. So that is the total length of our shaft. And with that, I think we can start designing, right? So this is the I-beam roller. Yeah. Okay, again, I need to change my units to inches, and I'll have dual dimensions to keep me sane. So I'll start, revolved part. I'm starting in the YZ plane. Okay, that's going to be the center point there. So what's the length of my shaft? It is 1.05 inches plus 1/16, that's the tolerance, plus 0.1793, that's the number 7 gauge thickness, right? So this is going to be the length of my shaft, right? Okay, and it's also going to have two different diameters, right? Look, we know that this diameter is going to be 10 millimeters because that's the bore of the bedding. So that's going to be 5 millimeters, right? Because it's a radius. But now we need to make more design choices, right? So if we go back into the roller, we see that we've got a little lip here. That's one element of the abutment of the bedding inside the roller. But I want my shaft to end at that face, right? To end at the face of this roller. So I want that 10 millimeter segment of my shaft to start from here and end there, which is the other constraining point of my bearing inside the roller. And I'll hit Control M, and in a straight line, that is 0.651181 inches. Okay, so that is going to be this length. Okay, now, well, I mean, this length is a driven dimension, but what is that diameter? Well, that diameter is going to be the abutment diameter. So now we're referencing the bearing PDF. And for the abutment in the shaft, it's lowercase d of A, which is a maximum of 15.5 millimeters. So basically, that's what I'm going to do here. I'll do 15 millimeters. I think that's enough. So I'll say that this is 7.5 millimeters. Now I have this picture here helping me when I'm designing in inches. We've got 0.29 inches. Do we have anything that's close to that? Well, yeah, I think 9/30 seconds. So that's 9/16, 19/30 seconds. Yeah, I'll go for that, right? It's a more standard number, I guess. So I'll go for 19/30 seconds, which the radius is going to be 19/64. Right. So that's a more standard number. It's within spec, so I'll be going for that. And with that, I have the main shape of my shaft. I have my sketches showing, which means I can select this line as an axis of revolution. Okay, this is my shaft. Now, as we said earlier, this is the abutment. That's where the bearing stops. Where is it going to stop on the other end? Well, on the other end, we need another circlet groove, right? And as with before, we'll go into McMaster Core. This time we need an external circlet, and that's going to be a metric one because the bearing is metric. External 10. So that tells us here, this catalog tells us that the groove needs to be of a diameter of 9.6 millimeters and 1.1 millimeters in width. And again, the thickness of the ring is 1 millimeter, so we have another 1/10 of a millimeter of a tolerance there. So that's how we will be designing our groove. I'm not going to download it yet, as I did in the roller. So I'll just go in here. I will imprint this. I've showed how to do that imprinting thing if you have a programmable mouse. If you don't, it's just a projection. Right? You just hit this face and you project it. Maintaining association. So this is going to be the rough profile of my groove. That is going to be a 9.6 millimeters divided by 2. That's the radius of that groove. The width is going to be 1.1 millimeters. And I know that it needs to be 14 millimeters from this edge, right? And I'll open up my hurl bar and revolve cut. That's it. There you go. Now, it helps to start the shaft going into the bedding if you have a bit of a chamfer there. It's not a bit. That's quite a lot. And that's not enough. Okay. And I also want a chamfer here. I'll just leave the same number. Chamfers in these turn parts make it easier for the machinists to handle them without cutting themselves, because you can get really, really sharp edges here with, if they have a bit of a burr, it's basically a cutting saw, edge, and it's going to bleed your hands. So, specify chamfers when you can, small ones, that's fine. Plus, on the back side here, this is going to be a welded part. So this is going to be a nice guide for the root of the weld. So that's it. We're basically done, but there's a little trick. There's a little advice I want to give you, and it's going to take us down a rabbit hole, but I think you should join me and dive right into that rabbit hole. So I will make a fillet on that inside corner as I did with the roller. That fillet is going to be 0.4 millimeters. Now, why am I doing that? Well, first, let's go into the bedding, the PDF of the bedding, and see that we're showing here an RA, a radius of abutment, and we're showing it on the inside corner of the shaft and on the inside corner of the roller. And to be honest, I should have specified that the inside corner of the roller as well. And that fillet radius is maximum 0.6 millimeters. And why is that significant? Well, it is significant because these things usually are made on lathes. And there's a thing called lathe inserts. So let's go again into McMaster car. We're just looking for specs here, and these are going to be universal. The shape of these inserts is very rigidly controlled. The formations you see on the top here, they're not cosmetic. They are the chip breakers. Different materials need different formations on there so that they break up the chip in smaller pieces, and that way we get a easier cut and a better surface. Whole another thing to discuss there, but let's go for carbide inserts for steel. And in here, this is a really nice picture to look at. But in here, we've got two things of interest. First, a nose angle, 80 degrees, sure. It can create that inner corner for us. And then we have a tip radius. Okay, so if we go in here, you will notice that we're getting 3 tip radii. One is a 0.008. That's really small. You can consider that negligible or 0. Then you get a different tip radius, which is a 64th. If we go in here, 1/64th is pretty close to 0.4 millimeters, right? And then you have another one, which is 1/32nd, and that 32nd is very close to 0.8 millimeters. And SKF specifies, and most bedding manufacturers do so, that they need 0.6 millimeter radius of fillet in that inside corner for the bedding to sit correctly. But our tool has a tip radius there, which means even though if we move it straight and up, right, it's still going to, at that direction change, it's still going to imprint its tip radius. And that imprinted tip radius is that little fillet, and I'm making it 0.4 because I need to show that in the print. I need to tolerance that. Also, I'm noticing that right now with this relatively large chamfer that I made, I am reducing the abutment diameter to just over 1/2 inch. So I'm going to make this a slightly smaller chamfer. So that's it. We made the shaft. And to make a 2 diameter evolution, we went through the design of the roller, specs on the bedding, cutting inserts for lathe tools, but you always need to think these things through. You need to be thinking about these things when you're designing so that your designs can be manufacturable. What you saw here today was a tiny little bit of DFMA, Design for Manufacturability. I hope you liked it. If you did, hit like, hit subscribe, and on the next episode, we will be designing the carrier, the main piece of the I-beam trolley. See you then.